be in time now. Okay. Yes. Okay. We are OMS, Optimal Management of Energy System. And here we have slides and okay. There are at least 10 tasks to be activated. So now you see the internal combustion engine. Okay. And now you should see the slides. Here we go. Okay. Okay, so we have 2 hours and 15 minutes. So, okay, first of all, I want to say that next Friday we could start our class at 11:30 in the morning of Friday. Are you in agreement with this idea, with this solution? I remember that was one of your requests.
Yeah, it's okay for me.
Is there someone against this proposal, this solution? All of you are okay with this new arrangement? Yeah, so okay. So I did not check yet with Professor Senatore, but I will tell him this, and I'm sure we will not have any trouble with this solution. So most likely from next week we will start at 11:30. Okay, so let's start now our class. I don't know whether you have had a chance to see to think about what we said in terms of methodological aspect of modeling. So the experimental analysis, analytical approach, numerical techniques, and integration within a single frame that could help us in building instruments that will help us in performing good management, good control, good monitoring of our systems. I will post on Moodle, so the elearning.unisa.it site, these slides in the next days. But just please tell me whether we may have problem. So let's start now and think about the fact that first, as we said, the approach which are experimental analysis. By the way, consider that experimental analysis, as we said, is the most conventional approach to use to be used for management and for the optimization of any system, of course. Analytical approach are where those most interesting, because they were able to reduce the cost. And consider that if you put together analytical approach and experimental analysis, when you move on the right side, for example, let me change. Suppose we are, when you move on right, or you may move on left, you may have, for example, an increase of the costs, okay? And on the increase of the cost, when you move on the left analytical approach, you have, oh, sorry, that's the problem of using these. Yeah, I have to remove this, go back here, and then set the pen. When, yeah, perhaps, sorry, I don't, it is better, don't change, yeah, exactly. So, when you move left or you move right, suppose that here you have a certain level of experiments that you need. If you balance analytical approach and experimental analysis, if you move in this direction, you increase the cost. When you move on the left, you go this way. So what does it mean? That if you use the best analytical methodology, let's say the best model, I don't know whether you are familiar, for example, with the Navier-Stokes equations, okay? I may ask you to switch on the camera. It's not easy for me to speak in front of a screen. If you could, I would appreciate if at least a couple of you may switch on the camera. So I will get the feedback of, and of course at the exam I will remember also your face, and please, whenever you will find me in the building, in the corridor, please stop me, say hello, and then I will be pleased to say you hello, to just tell me who you are. Otherwise, really speaking in front of camera is not nice. Okay, thank you very much appreciated. Thank you. So that said, when we move on the left side, means that we go in the direction of having only, sorry for this, I don't know what is the problem. Yeah, if we move on the left side here, we are in a position where only models are being used. Suppose that you are controlling or managing a fluid system, a fluid dynamic system. What is the best analytical approach that is absolutely precise and correct? Is, for example, Navier-Stokes equation in 3 dimensions. Okay, are you familiar with this? So you are able to understand this problem. This means that at this level, you need to write the Navier-Stokes equation, find the right boundary condition, integrate it wherever you are able to do this in an analytical way. Otherwise, you should move in this direction and go to numerical techniques in order to solve Navier-Stokes equations, and you have the solution of your problem. So this means that you have a cost in terms of what? Computer, cost in terms of brain, let's say. So skilled people, experts on fluid dynamics, experts on numerics, so brains basically. But if you move on the right side, why you increase the cost? Of course, this does not go to zero, let's say. This is the baseline, because this means that so you have certain level of cost here, which are computer, skilled people, and so on. if you move on the right side, so it means that you reduce the analytical approach with the simple model. Of course, you cannot solve a complex three-dimensional flow in whatever kind of pipe or in environment or whatever with the simple equations that are, for example, energy equation or momentum equation that are not in 3 dimensions, for example. Even if you reduce from 3D Navier-Stokes equation to, let's say, 2D to 1D, or even less 0D or whatever. Of course, if you move on right in terms of analytical content of your model, you increase the you reduce the accuracy of your model, and then if you move towards the right, then you reduce the accuracy of your model. You need more experimental data. If you increase the experimental data, you need to spend some money. You need a budget for what? For brain, of course. But instead of 10 engineers, you may need 1 engineer and 3 technicians, because you are investing on experimental equipment, benches or whatever kind of sensors or whatever kind of devices that can support you to measure data and then to do an experimental analysis.
Professore, non la sentiamo più. Cioè, almeno io non sento. Ah, ok, allora ho problemi con la connessione. Ok, ho problemi con la connessione, adesso cambio.
Probabilmente, perhaps it's a problem with your camera. So you are allowed to switch off the camera, at least you. If the others they have problem, just let me know, and then we will arrange. So I was just explaining it. When you move on the right side, and then you increase the experimental analysis, means that you are increasing the cost of equipment, and you are reducing the cost of the persons that are required to develop this, because instead of 3D model, you have the experimental data. And this is also a strategy of companies. Companies like, for example, Italian companies, they usually work with experimental analysis, because there is the approach of investing in equipments, because equipments, although they are rigid, they are more flexible than people. You know, when in a company you invest in more people, so you are hiring people, you may have a problem in the future. So, I mean, if you have a problem, for example, with your production and your market is going down, in Italy and whatever in in civilized countries, let's say, you have the problem of finding new job for people, because if your business goes down, your people they should find a place to work, and this is difficult. For example, you cannot fire licenziare in Italian people without any good reason. Whereas if you have experimental devices, it is more flexible, because you can sell it, and then you don't have the problem of having large amount of people working with you that should be fired because you don't have any business. I mean, but we are moving, I mean, a little bit out of the main topic, but this is a real problem that you may find in the real world. So if you move toward the experimental analysis, on the right side, you increase the cost of the equipment. But, you know, you have another problem, because, for example, flexibility could go down. Because if you do an experiment on, let's say, on a wind turbine of 10 meters diameter, and then you are working with another wind turbine, you need that. You imagine that you don't need any more 10-meter diameter wind turbines. but you may need 30 meters, okay? You cannot use the same data you used for testing 10-meter diameters, but you need to perform more. Whereas if you have numerical approach, analytical approach, you just change the diameter. So from 10 you go to 30, and then you have the data. So this is more flexible, less expensive, but perhaps in the ideal world, the accuracy you have here is the maximum. But for sure, the accuracy of your analysis goes in this direction, of course, because experimental data are the real data. Here you have simulated data. And for example, if you are working on non-Newtonian fluids, I mean, let me know whether you are following me easily with the example of Navier-Stokes equation. If you know that Navier-Stokes equation, at least I may imagine how you studied here, usually is given to the student with the typical Newtonian fluids, where the viscosity is a constant, or at least is a function of the temperature, or I mean, let's say that's a constant. But if you have a non-Newtonian fluid, viscosity is not a constant in the first. You know, if you see the problem from the very beginning. So means that if you are using Navier-Stokes equation with the constant viscosity for a non-Newtonian fluid, example, you are designing this kind of peristaltic pumps that are used for the circulation of the blood, or for there are those kind of treatment for in Italian is dialysis, is for you know, extracorporeal movement of the fluid. Okay, in one case, or biological fluids are not Newtonians. And then if you are designing a pump and you use Navier-Stokes equation, for example, with the Newtonian fluid, and then you consider that there is a blood instead of the water, which is a Newtonian fluid, you are making a mistake. Or a different way, perhaps you may measure on a small experiment, on a very basic principle, what is the viscosity at certain temperature, pressures, or whatever velocity of the blood. Then you can correlate the data with this experiment, and then increase the accuracy of your model. We are approaching now with this last example one typical case where you put together analytical approaches and experimental analysis. And the last approach I've given you is usually in the area of models identification. So when you go and your objective is to identify the models, the parameters of your model. Okay, we know what is the viscosity, but suppose that you are using another fluid. You are working in a food company. They are trading olive oil, or they are trading, let's say, jam. They are trading honey, or whatever kind of other fluid that is not water. Tomato juice, for example. For sure, we know in advance what is the viscosity, and we don't know the fluid dynamics relationship of the characteristic of this fluid with other variables like pressure, temperature, and so on. So then you may make wrong assumptions, and then you need to identify the characteristic of this fluid through a parameter identification approach, which entails the use of optimization techniques. So please let me know whether these examples or what I'm trying to give you as information is understandable. I don't want to say that it is easy, but let me know, because I mean we are speaking English. English is not my language. It's not your language, and just ask me whether I need to repeat some concepts. Let's move ahead. Here on the left side, there is a summary of what, or a partial summary of what I have said. And the first point is, when we said we have analytical approach and experimental analysis, because you may have, of course, Navier-Stokes equations, but you need some experiments, okay, in order to check whether your model, your numerical solutions are precise enough, are accurate enough with respect to your objectives. Yeah, and another point, as I said before, when we move from 3D to 2D, 1D, and this is summarized here, perhaps we are not precise enough with respect to the reality, but at least if the hypotheses of your model are correct, then you are having some at least information on the functional relationships, okay, between the variables, and in some cases, some of these relationships may be hidden by the experimental analysis. Yeah, numerical techniques, as we said, may support you in reducing testing, but this is just a straightforward consideration that comes afterward. So just to give you a short, let's say, joke, we will see this is from Professor Rizzo, who uses these kind of examples in order to make sure that you will remind these in the future. Okay, what is the concept, the model? The model is an abstract image, so an astrazione, we say in Italian, of a part of some aspect of the reality. So it's just a representation of the reality. This is the Coulomb law on mathematical models. What is the meaning of this sketch, this cartoon? If you believe that the model is the reality, it is like to go into the restaurant and eating the menu. Okay, so the menu is a representation of the reality. It's the abstract of the reality. And indeed, you may have, the menu is written, appetizers, main courses, dessert, and whatever. And this is a, very basic level for a menu. Then you may improve the representation of the reality. Okay, as appetizer, we have this, and this. For main course, we have pasta dishes, or I don't know, fish dishes, and as a dessert, we may have, for example, I don't know, cookies or any other kind of baba, profiteroles, or whatever. Okay, and this is an improvement of the representation of the reality. If we go ahead, we may improve the representation of realities by writing, let's say, for pasta example. Okay, pasta dishes, we have spaghetti with the tomato sauces, made with garlic or whatever, with the olive oil, with the salt and pepper and whatever kind of other ingredients. Then we have lasagna. Lasagna is very sliced piece of pasta with sauce, with meat or whatever kind of, and then you put the list of the ingredients. So you are improving the representation of the reality. Okay, and then, but still is a representation. Then the next step, what will be? Next step will be putting a picture of each dishes, and which is not very nice in a good restaurant. If you're good restaurant, you don't see all those pictures, but somewhere is very effective. For example, for ice cream or for pasta, you may have the picture of the dishes, and then you may, okay, Francesco Adinolfi is laughing, but it is true. It's like that. So, I mean, this is the best example I can provide you in order to show that the model is a representation of the reality. And your model, if you are a good modeler, you know the assumptions, you know what is the reality, so you know what are the ingredients, how are they made, and perhaps you are able also to know exactly, because you have had the chance to test each of the dishes, and then the way they are shown here could also support you in making this decision. Okay, if you don't like garlic, it's better that you take lasagna instead of spaghetti, because in spaghetti we cook this, or we have, or perhaps you may have some other, there are many different. So if you increase the representation of the reality, the model will be better, but will not be the reality, because on the menu, even with the picture and with the representation and the explanation given by the waiter, you will not smell the food, you will not taste it. This is the difference. And this is the concept. So if you go to the restaurant and you see a very nice menu, perhaps a kid, a boy, he see the ice cream may have the idea of hitting this picture, because it's very nice, very good reality. Okay, and there are examples that we can provide in order to explain and to put in your mind that the models are not the reality. But a good model should represent the reality in the best possible representation. And this is the case for hypothesis. When you write a model, for sure you should start from the hypothesis. We'll see this on if we move ahead. Another joke from Professor Rizzo, which is very interesting for those who performs experiments or build models. That theory versus experiments. Be sure nobody believes to a theoretical model except who has created the model. So if you do the model, you trust your model, you know the assumption, you trust your analysis, and you are confident. Others, they will not trust enough your model. We say, okay, this is just crunching numbers. When you do experiments, you will be the only one who will not believe, will not be confident on the experiment, because you know the limitation of your experiments. But for the others, mostly modelers, they trust absolutely your experiments. If you will be engaged with the modeling and the experimental activity, this is the truth. If you do a model, they will ask you always queries on how did you build the model? Are you sure? Did you account for this? Do you know that sometimes there are changes in the humidity that could affect the computation of your or data? You don't consider the humidity, but nobody's going to ask an experimenter doing experiments with an internal combustion engine and taking into account in the analysis of his experimental data, whether that day there was humidity or was dry air or fully humid air. For sure. I have had the privilege as a researcher in my professional career to do both experiment and measurements, and I say that this is true. This is completely true. So let's try now to understand what we are doing with the experiments and what are the traditional the limits of classical engineering approach. Let me put all together here at least the first two. As I said before, in a very quick exchange, I said that we use, for example, for fluid dynamic problems, we use three-dimensional Navier-Stokes equations, which are the basic equation, constitutive equations. And I said, if you are able to solve it, if you know the analytical solution, an analytical solution does not exist for Navier-Stokes equation. So you should move towards numerical analysis, and in most cases it's not possible to solve physical equations like 3D Navier-Stokes equations in a complete form. And this is one of the first limitations. Or even you don't have computational resource large enough to solve the problem in a complete form. So either the model is not does not have a solution, or you don't have the possibility to find the real solution. So this gives you the let's say gives you the way moving towards simplified approaches or simplified models that quite often are not enough representative. As we said before, if you have a three-dimensional problem, real three-dimensional problem, and you cannot do hypothesis of 1D model. If you use a simplified 1D model, you are not solving the problem. So this is an important point. So you must be able also to know, you must understand the physics, and you must basically and then you must understand. Oh, sorry, I don't know why this happened. Okay, let's do this way, it's better. So what I was saying is that if you want to solve the problem in 3D, because reality is 3D, you cannot do in 1D, unless you realize that the 3D problem is not fully 3D. For example, the flow moving in a duct where the length is 100 times bigger, larger than the height of the pipe, for example, of the diameter of the pipe. So in that case, it's easy to assume that it's not fully 3D, but it will be 2D because you have a profile, or even 1D. And then in this case, if you solve with the simplified approach, you are doing an error, you are introducing an error in your calculations, but it's not big error. But if you are in a square, in a cube, for example, and the air moving inside, absolutely you don't have the main direction, like in the case of the pipe. So if we use prototyping and experimental analysis, we increase time and cost, as I have said already before. If we move on the right side, I said before, we increase the cost and, of course, the time, which is a cost, of course. On the other end, you may have an interpretation of the physics with the empirical reasoning, or even if you are a good engineer, perhaps empiricism is not a good solution. Inference could support you, but inference is based on lot of experiments or the knowledge of the physics. Therefore, there is your, there is an influence and results are badly, they approximate badly the reality, and they are perhaps not replicable. So you cannot do this several times with the same results. This means in this case, for example, that you may have a low generality, so means that your model is not able to solve general problem, but only this specific problem, and then you cannot use your model for other things. We introduced the problem of non-Newtonian fluid. If you have a good model, you just change the relationship of the viscosity with the other independent variables, and then you may have the portability of this. So how we work in developing, I empirically realized that how to what happened when the screen disappeared. You will see now, perhaps. Yes, I realized. Empirically, I realized, so I should not touch the theme window. Sorry for this, but I was getting mad. I mean, one side of my brain was thinking in a parallel stream why this happens. So I realized. Sorry, I'm not a computer, of course, but this, likely I'm not a computer, but it's a way of approaching this. Suppose that we want to start to develop a model. Okay. Of course, we need a model structure, the definition and development process. Model structure means the structure of equation, how we define the boundary condition, and all the development phase. How from where we start? We start from a priori knowledge. So if we know that the fluid within a pipe has, let's say, suppose that this is a pipe. What we know in terms of, we know that the fluid moving from left to right. What do we know from this? We know that for sure at wall the velocity is equal, let's call it u. Okay, it's u is equal 0 here. Okay, we know that there is this velocity profile. These are assumptions. We know that there are stresses, and we know that there are some relationship between these stresses and the gradient of u along the y direction. Okay, u over dy as a function. Oh no, I have to solve this problem in order to make it perfect. Okay, this is u, and then okay. So let's move. This was u, and this is a constant. Okay, and this is a priori knowledge. And then, according to this a priori knowledge, we can improve the the results and the accuracy of our model. But I have to and to remove. Okay. This is the a priori knowledge, the state of art, and what we need more. We need experimental data when are available. So we start from the a priori knowledge, state of art. If we do the experiment on a pipe measuring the velocity profile, this could help, or experimental data for any kind of information. Of course, we need to know what are our objectives and applications, of course, because as it's written here, the mix of information sources that should be incorporated in the model is related to the objectives and application, and then the context of the work. Because if your objective is to design, for example, the length of a, the losses within a pipe, you need some information and you apply something. If you are not interested in this, but your interest is only in, for example, in the flow rate, which is a function of the velocity, or whatever kind of cases, that are needed for your application, you need to know what is the objectives and the applications. Means, for example, that you are working in the field of, for example, in the industry, in the food industry, and then you are using tomato juice as your fluid is a tomato juice. But if you are working in medical equipment and your fluid is the blood, okay, the objectives are completely different. The applications are completely different. Perhaps the objectives are the same because your problem is to move these fluids. The applications are different, so it means that you must be careful, because perhaps you should be sure that your pump should not generate, for example, air bubbles. If you have air bubbles in the juice, there is no problem at all. If you generate bubbles, oxygen bubbles in the blood, it may result in a very big issue and very critical problem for your patient. So, I mean, apologize if, because perhaps I'm making things too much simplified, but is a best way to connect this theoretical part with the reality. Okay. Then, of course, this is just, let's say, this upper part of this data, of this approach, provides you with the model structure, definition, and development structure, or whatever. But we don't have the model yet. The model is at the very bottom of this process, at the very end, and perhaps we can move directly from here to the model. But the best way would be to identify the parameters of our model. As I shown before, I said that the shear stresses in a fluid are computed as minus partial derivative of u with respect to y times a constant k, because we know empirically that is true, but we don't know this k. This k in the case of the blood or juice are completely different. And then you must identify whether this is the k for a juice, for a tomato juice, or is or is the viscosity for blood, or for even water. Okay, so what is model estimation or identification and invalidation. Parameter estimation means that you are comparing the results of your model with the results of experiment, and then you compare whether the results, experimental results, the numerical results, the model results, they fit with experiments. If they does not fit together, you should change the estimation of the value of your parameters, and then you modify the parameters until the model data and the experimental data, they fit together. This process is called parameter identification or model identification, because you are going to identify the parameters through an either iterative procedure, parametric analysis, or as we see through a optimization procedure, where the objective is to reduce the error between errors and model. And then you find the right parameter that minimizes the error. This is the last part of the process. So we see whether the model responds as a good response to the objectives, and to see whether it is right. So we started from some objectives. We wanted to have, for example, computer the losses, the pressure losses within a pipe of where we have tomato juice moving from one part of the plant to another part, from the reservoir, for example, to the machine where they put in can or in bottle or whatever. And we want to compute the losses. And then we do this with a model that is intrinsically precise and accurate, but is not accurate and correct and precise for this kind of fluid, because perhaps we made an error, introduced an error in the value of the viscosity, for example. Okay, so this means that the model is precise, is correct, but is not precise for our objective, is not satisfying the targets in our application context. So there are many parts of our process that may not be precise, okay, but for sure, if we have wrong knowledge of the project, of the problem, or we don't formulate precisely the objectives, then all the information, the hypotheses we have made are not correct. The model structure could be right, or the experimental data could be right. The process of experimental validation is okay, but validation on our experiment are correct, but perhaps it is not enough for our purposes. So, if the problem is fully 3D, for example, if we have made 1D model, it is precise, is correct with respect to state of the art, is correct with respect to model structure and definition. The experimental data we used, for example, in 1D are okay. Then we estimate the parameter, we validate it, the model is here, but is not enough accurate because we are looking for 3D model. Okay. One important point is the model classification. You have seen, we have already said that we may have different kind of model, and the simplest example I gave to you is the for example, is the 3D Navier-Stokes equations. Okay, and I have said that this is the best representation of the reality. So means that we are very close to theory here. For example, here we have 3D Navier-Stokes equation. Okay, so you are here at the 3D Navier-Stokes equation for the problem, or I don't know, any kind of complex problem like Navier-Stokes equations, or you are doing compressible flow, and then you have correct equation. And this is one side, okay? On the opposite side, we have representation based on experiments. As I said before, if you want to build models, you may rely on the theory or on experiments. So this means that here you should solve complex equation, integrate complex equation. Here you must put in place experiments, cost, people, treating data, and so on. And then you build your model on experiment without theory, and then here you build your model without experiment. So it is, for example, without experiment, without theory. Engineers, mechanical engineer, for example, the problem of the 3D Navier-Stokes equation, or fluid dynamics, or chemical problem, or mechanical basic problem, you try to solve and develop your model starting from the theory, because you know the theory. Most likely happen that in some cases your colleague from electronic engineering, an electronic engineer, or computer science engineer, okay, I have a lot of data, I need the model, very simple, I can do the model very simple way. I just put all the data in very advanced technique, in very advanced computer, doing machine learning, deep learning, or neural networks, or whatever. And then I will come out with a good model with very high accuracy without knowing anything. So be careful. Be careful, because for sure this may have loss in generality, because it depends on the experiment. So if you are able to present to the model all the experiments, okay, possible, available in the real life, your model, if well done, is the best model you may have. It is fast, it may need a big computer. But if you don't have this, theory could help you. Theory could help you. It could say, okay, look, this experiment that is meaningless, because it doesn't provide you any information more than those you may need. So, sorry, I have to remove all. So the white box theory, as I said before, is our models are based on theory, 3D Navier-Stokes equations, as I said before. Black box models are based on experiment. So these are based on a priori knowledge, okay, and these on experimental data. These are more representing physics, so they are said as phenomenological, and these one are called black box or synthetic, because they are synthetic in terms of number of let's say equations. They are synthetic in the terms of synthesis of the problem. Here you may need a lot of data. In the middle, we have the gray box model, of course, which is a mix. Of course, when you mix white and black, you have gray. Here, in gray box models, for example, we use simplified physical description. Okay, so we know that, for example, for a flow in a channel, in the reality, we need three-dimensional models, three-dimensional representation, whereas we don't have enough resources to integrate it to solve 3D equations, but we are able only to do 1D equation. So it's not precise, okay? But we may so for example, we moved from 3D to 1D, and then we put some experimental data for parameter identification. So your model is 1D plus some parameters that are identified by through the experiments in order to compensate for this lack of knowledge. So basically, of course, we also said that, for example, computational effort increases in this direction, okay? So perhaps you may need intermediate computational effort. So on the left side here is the computational effort. You want to reduce the computational effort because you need, for example, a model running on real time, representing the real phenomenon may take should take very low computational resources, so it should be very fast. So in this case, you may use, for example, 1D model, which is simplified, so it is easy to integrate, and then you may correct the result through some parameters beta that you should identify. So the model parameters compensate for the missing information from the physics. Of course, there are okay. You may apply several approaches. You should put together many approaches. So you may have a big model where you may have a 3D model, 1D model. Suppose that you have. Let's give an example here. Suppose that you have a duct you have some flow here. Could be water, could be air. So here you can apply easily 1D model. Okay. Here, if the length suppose that this is oh, okay. Okay, it's not very precise, but I hope you understand this. Suppose that this is, for example, 1D, and here you may imagine to have in the core of this fluid, here, you have 3D representation. But if this length is length enough, so let's say that this L, this is H, suppose that L is greater than 10 times H, perhaps you may imagine that the flow is 2D instead of 3D. You are following me. You are understanding what I'm saying, okay? Yes, are there any problem? Are you okay with this?
Yes.
Yeah, okay, thank you. So just try to be. Is it 3D? Instead of if L is 10 times the 8, for sure you have a flow that has could be 2D in this in the direction, let's say X, Y, or Z, 2D in X, Y plane. Okay, so you can simplify the problem in from 3D to 2D problem. Okay, here will be 1D, for example. This will simplify. Of course, it will be rather complex because this surface here and this surface here, there will be boundary surfaces for this cube, and this surface will be the boundary for this 1D problem. Okay, it may be complex, difficult to implement, but for sure will solve the problem in a very quick manner. Okay, I don't know whether what I'm saying it is clear and understandable, and then you are confident with the understanding of the problem from your side. Okay, so now we stop for 5 minutes, then we resume the lesson, and then we stop at 6:30. Okay, please come to me with your comment. Mr. Hernandez, is that clear? Is everything clear from your side?
Yes, it's clear.
Okay. Just stop me if you don't understand. I don't know whether I'm using. I'm not a good English speaker, but perhaps some terms you may not understand, or I'm not clear, or whatever. Just stop me and don't worry. Okay. Good.
Okay, sir.
So thank you in 5-10 minutes. Okay. Thanks. Okay, are you there?
Yes.
Okay, thanks. Okay, this was the slide, of course. We seen before, so this is the classification of the models, and I was explaining you, as you remember. So we stop here speaking about the mixing of 1D and 2D model, for example, here. But you may have also other approaches, and you can simplify because you need computational time or things like that. So if we move ahead with this, let's try to analyze one model. Let's apply to the case of internal combustion engine, for example. The design of an internal combustion engine. You may remember some of the main concept. You know what is an engine, okay? Then this is the structure. So the structure we explained before. For example, at this level, so objective and application, we may have a virtual engine, and then we want to have a virtual engine for the design of a new one, where at this level we don't have a constraint in terms of computational time. So here we have all possible a priori knowledge which should be included into the model. For example, here we use a white box approach. For example, three-dimensional models with combustion, for example, this level. And at the end, we will get very generalized and predictive model to be developed. So what are the main ingredients here? We need all the knowledge into the model. So turbulence, chemical reactions, fluid dynamics, thermodynamics, all heat exchanges problem, and multi-phase flow, because we are taking into account evaporation and all the physics within a model. So you may imagine. And the objective is for the design is to have a virtual engine. So virtual engine a virtual engine means that it's something that is able to represent the reality. So finally, what is the application? So the structure is a white box model, as we said, 3D, chemistry, and so on. And this is a very generalized and predictive model that will be developed and used. Suppose that our objective is not the the design anymore, but is the control. So you know what is the difference, okay? For design, we need to identify the displacement, the length of the connecting rod, the bore, the number of valves, the diameter of the valves, the length of the pipes, the kind. I mean the cams that open and close the valves. What is the the advance of the opening valves and the retarding of the closing valves, let's say the shape of the combustion chamber, all these, problems related to the sizing, dimensioning of the device, in order to have a good combustion, in order to have a good release of energy and good conversion of thermal energy in work. Whereas if we move in control, we see that first of all we need real-time engine control, because in the case we had before, for this application, we don't have no constraints in terms of computational power and time. This means that in order to design a good engine, you may need 1 week, 1 month. In the design process in a company for a new, really brand new engine, they start with a 3-dimensional Navier-Stokes equation, fully integrated with the combustion chemistry, 1D flow in the ducts and so on. And they perform, let's say, simulations with the 10, 15, but 15 is really a large number, kind of different combustion chambers, okay? Which is the main problem for combustion, of course. Then, through the computer, they identify among those 15 combustion chambers, 3 main chambers. They are performing very well. The shape, for example, just to give you an example, would be something like that. Okay, of course, this is becoming a nightmare. Okay. Yeah. Well, it's crazy. So means that the first, for example, this is your cylinder, and then the shape of your diesel engine. Okay, sorry. Will be an omega shaped piston, or could be a ball like this one, because when you have the jet, you want that the jet moves in this, the flow injected moves in this direction, whereas here the jet could have this flow, or could be an open ball like that, and then you may have multi-jets and so on, and then your shape of the head, the combustion chamber could be something like that, or if the case, or where you are going to put the spark plug, if there is SI sparking ignition engine, or where to put the injector, or what should be the angle of this this head, or whatever kind of things, and then in order to do, and then you select these 3, and then you build 3 models, 3 engines, physical engines with single cylinder, and then you do experiment, and then you decide. When you do control is a typical problem as we analyze. Suppose that this is your internal combustion engine, and you need to control your control variables. This is your output variable, which is your target, and then you have some state variables. You may have some disturbances or whatever, and then this is your control, electronic. This is your control. 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 This is your electronic control unit that reads this information, may take information from disturbance. This is your target, and then here there is a controller, basically a model basic controller, or you may have maps or PID controller. So what is the main problem? The main problem is to have your electronic control unit. You may consider that in time you may have suppose that these are let's say this is 1 revolution, 2 revolution, 3 revolution, 4 revolution, n revolution. So at each, if it is a 4-stroke engine, every 2 revolutions, you must know exactly what you should give in terms of control variables to your system. You should give the information to the injectors, the spark ignition, for example. You should control the EGR valves. You should control, for example, let's say the pressure for the injection, the spark of the injector. Sorry, the advance, the crank angle in advance. You may inject the fluid, and this has to be computed every 2 runs, and then you must actuate every 2 runs. So this means that if you are running at 6 RPM, which means 6,000 RPM, means that you have 100 runs per second. So every in 1 second you have 100 revolution, means that 1 revolution occurs in 100 of second. Okay, so every this is okay. So sorry, that's in this interval time you have 1 revolution. Of course, if you should do this every 2 revolutions, this will be 0.02 seconds. And within this time frame, you should be able. So let me clean a little bit. So every 2 revolutions, you have, so in one computation, so it means that in every 0.02 seconds, you should be able to measure your y, real y, enter into the ACU. This is your target here, and then you measure the disturbance, okay, and then you must be able to compute the control variables to be applied after or at the beginning of this. So you may imagine that, do you understand that it is not possible to use, for example, a model-based control where you have, for example, 3D Navier-Stokes system of equation? No, it's unbelievable. Are you in agreement with me? You understand what is the problem? So it means that here you should put very simplified models that are able to run, unless you have thousands of parallel chips working at the same time. But you are doing this in electronic control unit, which is a device like this one, big, is not a supercomputer, and then you cannot do that. So you have thousand and thousand of operations to be done at the same time. So let's go back, of course, to my nightmare. Yeah. So for engine model, an engine model for control, you need real-time control. So it's a severe constraints active in terms of computational power and time, and of course a lot of model reliability. Because if you are driving the car and your model-based control is not able to say, okay, look, instead of injecting one quantity, let's to inject less quantity of fuel, and then you accelerate in order to overtake a car, and instead of accelerating, you are slowing down with respect to what you expect, because there was a wrong computation, there was an error or whatever. Your model is not reliable at all, because it does not provide you the output it is needed by the control, the control system. You may have a lot of knowledge, but you cannot include this in your model. You see here. So you have the knowledge, you know all problems of combustion, emission formation, or whatever, but you are not able to put this within a controller. So this is a limitation. What is the approach, the structure? You need a black box model, at least, because it's very fast, is not time consuming, or eventually you may go ahead and move in the gray box approach with the large use of experimental data. What is the results? Following this path, okay, objectives and application. What is the state of the art, and the a priori knowledge? What is the structure definition? You have a black box, gray box, and so on. The final result is a very fast and reliable model. And the model will be dedicated for the engine and cannot be generalized to other engines. Why? Because we are using a black box model or gray box model, and we use experimental data taking on taken on the engine we want to control. So the model-based control is specialized for your system and cannot be easily used. For example, if you are developing a control unit for a let's say a Fiat Panda, you cannot use the same model for a Ferrari or for a truck, because the performance of the engine are completely different, and the knowledge taken from experiments and which is put in the ECU, electronic control unit, to the control model, model-based control or whatever you said there, experimental maps and so on, are completely different. Because, for example, Ferrari runs the engine as maximum engine speed up to, let's say, 8,000 RPM. The Panda, it does not go up to 4,500 RPM, or a truck does not go above, let's say, 1,500. So at least, you know, the field of operation is completely different, and then cannot be used. So, is there any doubt on this? Do you understand? Are you following me in this analysis? Please. Okay, very good. Oh, I don't know what happened. Sorry, I have to solve this problem. Now I cannot show at the same time. Yeah. Okay. If we go back to the model classification, we must consider the modeling approach we have seen before. So we have a phenomenological model, which are white box model at one end, and the other end we have synthetic black box model. So we have mixed gray box in the intermediate level. So we are hard disciplines and soft disciplines. Because phenomenological model, we introduce ordinary or partial differential equations, complex techniques, whereas for synthetic black box model, soft disciplines or experimental data and mixed are in the intermediate position. About the feature, so in terms of a priori knowledge, we need a lot of a priori knowledge for phenomenological model, whereas for synthetic model, we don't need any understanding of the phenomenon. So this is more for computer science engineer, for electronic engineers. There are a lot of methodologies in order to use the data, to shake them mathematically, and then to obtain results. Objectives, phenomenological model can be used for application like the one we showed before in terms of the design of the engine, but also to understand the system, so for knowledge purposes. whereas synthetic black box model can be used for straight application like the control, for example, for management. For phenomenological model, we have computational effort very high, where synthetic black box model, they don't need very large computational effort. The synthetic black box model, they need a lot of experiment, as shown here. Experiments in phenomenological model, we may also avoid to use experiments. Of course, it's not the case, but it's very just few experiments. As I said before, the example I gave you on the design of the system, as I said, we start from 3, for example, 15 white box model outputs, okay? And then we converge to 3 main solution with best performances. And then we end up with 3 of these, and then we do experiments on these. So, as we said before, at the very beginning, we start without knowing experiments, okay? And we don't need the experiments in order to set these 15 models. Models now is models, not mathematical models, but it's real speaking in terms of physical models. Then we build 3 physical models, and then we test on experiments. Whereas on synthetic black box model, we need a lot of experiments. And then, in terms of predictivity, we have this phenomenological white box model that are very, very high predictive, because since we are not limited by experiment, we may change, for example, the bore, the diameter of the valve, this angle, this shape, as we said before, what will be the angle of the but we know already that this white box models have better generalization and predictivity, but they usually require large computational effort, as we said before. The validity of a black box model is usually limited to the set of experimental data for their identification. If we identify the list of the evaluation criteria. So if we have a model, we must identify, we must consider, we must evaluate, assess the capability of the model. Here we have the physicalness, the precision or accuracy, but we must be careful because precision and accuracy, we can use one instead of the other, but there is a precise meaning in precision and accurate. generalization, which is the predictivity, any possible chaotic behavior. They should be identified. They can be identificability is one of the performance, simplicity, and the so-called balanced precision. And then I will show you some detail afterward. In the first, for the first property, the model should be the good representation of the reality. So it's the case of the menu. So if the menu is so good representing, you may have the idea of hitting it, but it's not the same. So it's the best representation of the reality. Why? How could we do that? By introducing the all a priori knowledge, which is included in the model. Then the accuracy or precision. There are two differences. So in some, we put all together, but there is a difference between precision and accuracy. I'll anticipate this to you in this way. Suppose that you have a target. Okay. Then okay, let's try. I don't know whether you know the darts game. Do you know what I mean? The darts. What are darts?
Richard.
Okay, exactly. But I don't know in Spanish how do you call it darts. Recette. How do you call it?
Dardo.
Dardo. Okay. Let's take a dardo. Two kind of darts. One is let's say, is a black darts, which is a white box. Okay, this is the results of the. Okay, this is an error, of course. This is a black box model. This is a white box model. Okay. Well, actually, we don't need this classification. Sorry, let's leave like this. This is the dart for white box model, and suppose that we do one simulation on one system, and we are here, the first dart. The second dart goes here, the third here, the fourth here, the fifth here, and so on. So if you compute the error as the distance, let's do this in this way. So what will be the error? The error will be, let's say, the distance. Oh, sorry. This distance is the error. Okay. Each test you have an error. If you have the distribution of your error with the one model, the black one, you have suppose that this is the error, this is at 0. Okay, and your error distribution will be this one. Are you following me? Okay, this is very basic statistics. And then this is your sigma. Okay, if you build another model, let's say violet one, and then this result of your violet model is this one. How you can assess the quality of this model? What you would say? First of all, there is in the average, there is a big error. Okay, so let's say let's call this is model number 1, and the violet one is model number 2. Okay, then the distribution you have, this is the average error of number 1, and this is the average error of model number 2, which will be some number. Okay, what will be the distribution? Distribution will be like that. Do you agree with this? Okay, what does it mean? So this is sigma 1, this is sigma 2, so epsilon 1 is less than epsilon average 2. This is equal 0, let's say. Okay, then sigma 1 is greater than sigma 2. So what you would identify in terms of precision and accuracy. Model 2 is very precise because it repeats the same results every test. Model 1 is very accurate because in the average he has 0 error. Model 2 is not very much accurate because it has an error epsilon in the average. Epsilon 2 is greater than, is very large, let's say. Suppose that this is the 10% line, this is a 5% line, this is 2% line. So it means that model number 1, the error is always less than 2% for sure. Model 2 is, let's say, 7.5% error, but you are sure that it will be always 7.5%. So if you need, for example, you can correct the model by adding some parameter. You are sure that the parameter will be only 1, because you are sure that always the error will be epsilon 2, which is 7.5%, whereas the other model, which is very much accurate but low precision, the parameters in order to correct the error will change every time. Because if it will be, let's say, plus minus sigma, if you are here, your sigma could move result here, not necessary there. Perhaps this is too much advanced as a concept, but this is the representation of the accuracy and precision. Okay. In most cases, we use as, interchangeable. They can change. We can use one instead of the other, vice versa. But this is not the correct way to go ahead with. Okay. Generalization. Generalization is a very important point because it gives an information of the predictivity. Suppose that you developed your model. This is a typical for black box models. You made the experiment on a Ferrari, and then you developed the model based on this data, and then you want to apply this model on a Panda. You cannot translate the data from a Ferrari to the Panda because they are completely different engines, but they could be, we can call it plants. If you are an industrial plant and then you are acquiring data, for example, for the plant producing Coca-Cola, and then you want to apply the same model based on the experimental data to the tomato juice plant. I'm not sure you will be able to use the same model from Coca-Cola to the tomato juice plant. Whereas if your model is based on physical information, for example, how much costs in terms of energy producing a Coca-Cola, and how much energy you need to produce the juice, the tomato juice. So you go on the tomato juice plant, and then you measure the fuel, the energy consumption, and then you see how many liters of tomato juice have been produced. So, and then you will have, let's say, just doing numbers, 10 kilowatt hour of energy per liter of tomato juice. Okay, this is my model for a liquid to be, handled by a set of machines and to be put in a cans or in bottles or whatever. You go on the Coca-Cola plant, and then you apply this model based on the experiment. Does not work because you will realize that perhaps Coke plant, I'm not an expert of this, but perhaps this will be 5 kilowatt hours per liter. Why I say that's less? Because the viscosity of this tomato juice, the viscosity is is greater than the viscosity of Coca-Cola. It makes sense, actually. I don't know. Tell me whether you do not agree with this. So this means that in order to move the tomato juice throughout the pipes, for sure it will cost more. That's why you spend more energy. So if you start with the tomato juice plant model and you start to build a Coca-Cola plant using the same model, you are going to undersize the dimension of your energy system. That's completely wrong. So you are setting, for example, the dimensions of the cables of electrical lines. And then here, your problem will be here, for example, that the size will be too small. Then you start running the plant, the machines and then it will burn everything. So implicitly, if you use a black box model, you must take into account for these correction factors. Whereas if you start with a white box model, you know that the viscosity of tomato juice is greater than the viscosity of Coke or water or whatever. So you know that energy, in order to push the fluid through the pipes towards the bottle or can machine, it will cost less in Coca-Cola plant. And then you can use small wires, it will cost less. Is this example fine to you? Do you understand? Okay, so this is the model. So I use the model of the Coca-Cola of the plants because we are in a course of smart industry engineering, not smart cars, and optimal management of energy systems is based on this. It's not only management but also design of the system. So this means that black box models are not easy to be generalized and cannot be, applied to any other system. Chaotic behavior. Chaotic behavior is something something related to, let's say, the example we explained before, okay, which is this one with darts. You can say why we have this distribution, because inputs you are providing to the model, they are always the same, but don't forget that you are in a computer system. There could be some rounding errors in the machine. The representation of the numbers in the machine, they are, let's say, chaotic, or you are using real data information. So you want to see, for example, what happened if the external temperature changes, and if your model is not precise enough, it may spread out. Okay, because if you develop the model for 10 degrees Celsius and then you tested at 20 degrees Celsius, when you go to 30 degrees Celsius, perhaps is not linear, and you may have differences. Okay, and an accurate model with less precision could have a problem in chaotic behavior. But I've just given a very trivial example. If you think about, for example, complex equations with the nonlinear behavior of the equations, it is showed that if you change the initial values, you may reach different solutions. I don't know whether we will have the chance to see this example I'm trying to provide you with. When you use nonlinear models like neural networks, if you change the initial conditions in the parameters and then you identify these parameters against experimental data, the parameters at very end with the same error of the model could be different, because this nonlinear interaction between parameters and data, so you may land in a situation like this one. We will try to see this example in the future, but suppose that you are if you do a parametric analysis, suppose that you have your model y is a function of x and a set of parameter beta 1 and beta 2. Okay? This is the real model, which is reality. Or let's, sorry, perhaps it is better to say g of xy, okay? And then this is the real measurement, and this is real measurement. So means that you are showing, suppose that you have a relationship y is a plus b times x plus cx squared. If you put in your computation yeah, could be whatever kind, okay? Times c. What does it mean? This is your theoretical model developed with your experimental data. We used this data, and then you identify these parameters. Okay. If you design or you represent the error as a function of y, let's say epsilon j minus j or I. Okay, I means the number of the independent variables. Beta 1, beta 2 are the parameters, and j goes from 1 to n is the number of experiments you have done. So you suppose that you want to represent your error in a 3D as a function of beta 2 over beta 1. Okay. What happened? Suppose that you have your error here. This is a value. So suppose that you will be able to represent the isolines, the curves with the same error. Okay. This is one value of the error, another value of error, another value of the error. So you may have sort of autocorrelation between the parameters. So with this level of error, you may either use this value of beta 1, this value of beta 2, the error will be the same, or this point, at the same error, you may use this and this. This is one of cases of autocorrelation of parameters, but there are many. Okay, we are running almost out of time. I think I should go to the end now, and perhaps next time we will repeat this part. We started from chaotic behavior. So if you have different non-linearities, let's say, you may have impact on the parameters, and that's what I shown before. But you may have also problems in the data according to the initial value because of the strong non-linearities of your model. Perhaps we will not have chance to show you this example, but I can provide you with some information. Then before ending, we should talk about identificability. For example, the model parameters and the statistical significance, which I have just introduced with a bit of statistics, but are other problems. The model should be simple, because if you put a complex structure that is not needed, and then you assume more parameters, you are going towards the so-called problem of over-parameterization. If you over-parameterize your model, you are losing, for sure, at least generalizability, and then the predictivity in those regions where you don't know the example. But we will come back to this. I mean, this is a quite dense slide, and we can explain this better in the next class. We will take this on Tuesday morning. I don't know whether there are comments on these. Sorry. Are you okay? I know that this class was quite dense, and we will repeat this, but you will understand this, and then I will just suggest some reading if you have it, or you have the chance of looking at Draper. No, sorry. Sprit and Van Kiste, sorry, which is a very good book for this basic.
You write the name in the chat.
Say it again. It is very old.
Write the name in the chat.
Say it again.
The name of the book. Could you write the name of the book? Potrebbe scrivere il nome del libro nella chat.
It's not. It's not. Yeah, let's do this way. It's this one. Sprit.
Okay.
Advanced Kinster. Modelli matematici e simulazioni. This is in Italian, but this is the translation of book written in English. Let me know whether you are able to find it, or I don't have it, or should check whether I have the digital version. Anyhow, let me know whether you will find it. For sure, I have, not me, but Professor Rizzo should have the paper version of this book, which is very, very interesting. Okay? So let's see next Tuesday, and enjoy the weekend. Okay. Bye.
Thank you. Goodbye.
Thank you, Professor.
Bye. Bye.
Bye.